Hello, students. I have to introduce to you a topic which is absolutely new to you in a manner so that all of you follow it clearly and precisely. In order to make this course interesting to you, I shall, to ensure that I cover almost all the important points, I would make use of notes as well as PPT slides. This would ensure that I don't miss out on any crucial information that cannot be included in the PPT slide. This therefore would require me to glance at times at my notes on the table in front of me. Please excuse me if this would distract your attention. However, at the end of the course, let me assure you that all of you will fall in love with lasers. So then, straight away into a course on an introduction to lasers and laser systems. Students may have taken a course on lasers, while others may not have had the opportunity. To ensure that this course is accessible and engaging for everyone, we have designed these 5 lectures spanning probably a week to provide you with a foundational understanding. Be assured you will only need a high school level physics background to understand and gain a clear insight into lasers, what they are, how they work, and what makes the light they produce so special. See, early this century, nature brought out a unique volume to unfold the 21 major scientific discoveries of 20th century that changed the face of science and enthroned the world. The foreword of this book was written by Steven Weinberg, who received 1979 Nobel Prize in Physics for his pioneering contribution towards unification of electromagnetic and weak nuclear forces. Laser incidentally figured as the 8th article in this volume, written by Charles Townes, who won the Nobel Prize in Physics for his pioneering contribution in the development of lasers. Most of the important attributes of a laser I have tried to capture in this slide. Let me read them out for you. Laser is an elegant and yet awesome tool that has provided seemingly magic solution to almost any problem since its invention in 1960. Powerful lasers can slice through heavy steel as if it were cheese. And even more powerful lasers can destroy an aeroplane in the flight. A delicate laser, on the other hand, can stop bleeding deep inside a patient's body or can repair a detached retina in the human eye. A very handy laser, as you all know, reads supermarket barcodes. Laser can also help measure the distance to the moon with incredible accuracy that can be better than even 1 part in 20 billions. It, of course, makes use of the range finding principle to measure such a distance. And most importantly, it has the potential to harness the power of fusion to generate clean energy for humankind the way sun makes for our solar system. In this context, it is important to note here the recent finding by the researchers at National Ignition Facility of Lawrence Livermore Laboratory located in California of self-sustained laser fusion. This finding is regarded as the most remarkable scientific achievement of the 21st century that forms a crucial milestone in humans' quest to replicate the process that powers the sun and stars of the universe. However, the priceless gift of the lasers to humanity is undoubtedly the all-light fiber optics communication, the backbone of today's communication network that have made possible the bridging the continents in the blink of an eye you take a mobile phone today and connect to any individual, be it your friend or relative, in a flash, regardless of their location, wherever they are located on this globe. Instead of diving straight into lasers, it would be worthwhile to take a brief detour to understand the working of a quantum source of light, which many way mimics the operation of a laser. Laboratory studies involving such sources have often made groundbreaking discoveries. For instance, the exploration of photoelectric effect, which occurs when UV light emitted from a quantum source of light shines on a metal, and made from the metal photoelectrons are emitted. The exploration of photoelectric effect by Einstein actually cemented the quantum concept of light, and it fetched Einstein a Nobel Prize in physics, not for his work on relativity, which is more commonly associated with his name. Similarly, in 1928, C.V. Raman used another source of light, a mercury vapor lamp, and the photons emitted by this source, upon scattering from some appropriate medium, can both give energy to the scatterer or even gain energy from the scatterer. When this is scattered with an energy gain, that is called anti-Stokes-Raman scattering. And when the scattering occurs where the incident photons actually deliver energy to the scatterer, that is called Stokes-Raman scattering. This profound discovery fetched Raman the Nobel Prize in Physics. Example of a quantum source of light is a fluorescent light. Typically, let's see how does a fluorescent light work. A discharge tube here contains some neutral atomic species that we call A for our convenience, and these species are taken at a very low pressure. And although neutral, you can't avoid presence of at least few stray charges for obvious reasons. The cosmic radiation that reaches Earth's surface from outer space is actually responsible for this. Now, on application of an appropriate voltage, by placing longitudinally, by placing two electrodes at two ends of this discharge tube, the stray electrons in particular will experience a force which is given by the product of the electron's charge and the applied electric field, which basically is the ratio of the voltage applied between these two electrodes and the spacing d between these two electrodes. And as the electron moves, it in this force, and the electron thus is accelerated with an acceleration which is given by the force, ratio of the force, the acceleration. Electron being much lighter, therefore it receives, its acceleration is pretty high. And as the electron moves, it thus acquires, it thus gains velocity because it is accelerated and thus acquires kinetic energy. If the electron, after acquiring sufficiently high kinetic energy, collides with a neutral atom, then the collision may result in ionization of the atom, wherein an additional electron is also created in the process. And having supplied the energy of ionization, the original electron now moves with reduced kinetic energy. There will be many such ionizing collisions, resulting in creation of an avalanche of electrons in this discharge tube, which manifests as a flow of current. The ions, being much heavier, have negligible contribution to the flow of this current. However, some of the collisions that the electrons will have with the neutral atom can also be inelastic, in the sense that part of the kinetic energy of the electron is transferred to the atom as its internal energy, and the atom in turn gets electronically excited. And after spending a finite amount of time in the excited state, the excited atom eventually comes down to the ground state, releasing this excitation as a quantum of light, the so-called photon. These emissions are actually random in nature. That means the photons are emitted all along, in every direction, over the entire 4 pi solid angle around this discharge tube. Therefore, light from it spreads everywhere. It travels in all possible directions, and that is why this device can be used as a viewing source. The obvious question that can be asked here is that, can all these excited atoms be forced to emit photons in a particular direction, so along the axis of this discharge tube? If they do, then you will have a unique beam of light coming out of this device, hitherto unknown. The answer to this question, as we know now, is a definite yes. Einstein knew this answer way back in 1917, when he first envisaged the possibility of stimulated emission. But the important point that I would like you to note here is that if all the excited atoms can be forced to emit photons along the axis of this discharge tube, then you will have an extremely powerful beam of light coming out of this device, because now the photons do not travel in any other direction but along the axis of this discharge tube. True, the device cannot be regarded as a viewing source anymore, because light now don't travel from it in any direction other than along its axis. However, this unique beam of light will have many fantastic properties that can be put to our day-to-day life. Mr. Einstein spoke of stimulated emission in 1917, but it took more than 4 decades to exploit stimulated emission to manufacture such a unique beam of light, when Theodore Maiman, an American physicist, invented laser, a ruby laser, in 1960. The name Einstein is synonymous with relativity and also the famous mass energy relation EMC square, which is regarded as the most famous physics equation, and also to some extent with his explanation of photoelectric effect that incidentally fetched him a Nobel Prize in Physics. However, it is much less well known that the concept of stimulated emission, which has given birth to a device that now has practically pervaded every walk of our life, is also his brainchild. Before I tell you about the realization of stimulated emission in an experimental system, let me very quickly take you through the processes of spontaneous and stimulated emissions. Let's begin with spontaneous emission. A photon shines on an atom which is in its electronic ground state. This is the nucleus of the atom. If the photon has just right amount of energy, which is of course h nu if its frequency is nu, then it can electronically excite the atom for a while. The excited atom, after spending a finite amount of time in the excited state, will eventually come down to the ground state, releasing this excitation energy as a photon. These emissions are random in nature, therefore the photon can be emitted anywhere around the 4 pi solid angle around this atom. Such an emission is called random or spontaneous emission. Let's see how does stimulated emission take place. We consider photon that we call photon 1, which once again excites the atom as before for a while. And when the atom is still in state of excitation, a second photon that we call photon 2 now interacts with it. And now the excited atom instantaneously comes down to the ground state, releasing in the process a third photon that we call photon 3, which is identical to photon 2, the stimulating photon in all respect, and most importantly, they travel in the same direction. Such an emission is called forced induced or stimulated emission. It is obvious that the seed photon, that is this photon 2 stimulating photon, originates from the spontaneous emission itself. Now returning to the example of the tube light, let us explore if a tube light can produce a beam of light by exploiting the property of stimulated emission. You see, the photons emitted due to spontaneous emission by the excited atom travels in all possible directions, that is shown here. However, the photon that happens to travel along the axis of the tube light will stimulate the maximum number of excited atoms to emit identical photons along the same direction. And this is not the end of the story. All these photons emitted due to stimulated emission traveling along the axis of the tube by default cause further stimulation of excited atoms on their path, leading to a multifold rise in their numbers. Thus, ordinary tube light, if this were true, the ordinary tube light should also be able to give an intense beam of light as a result of amplification of those initial few spontaneously emitted photons that travel along the axis of this tube light. Certainly, this is not true, else the tube light would have come into existence along with the fluorescent. Certainly, this is not true, else the laser would have come into existence along with more than a century ago, along with long discharge fluorescent tube lights. So, where lies the fallacy? To resolve the fallacy, we consider an ensemble of atoms that can reside in two energy states. One is the ground state or lower energy state, the other is an excited energy state. Now we have an ensemble of atoms. And we consider for these two situations. In the first case, let us assume that the excited state has population which is less than the ground state population. And this is the type of system that we normally encounter in nature. And now we shine this medium by a beam of light that comprises of a bunch of identical resonating photons. Identical resonating photon. By resonating photon, I mean that the photon's energy matches exactly the energy difference between these two energy levels. Therefore, as this beam of light with containing this identical resonating photons traverses through this medium. They will interact with atoms both in the ground state as well as excited state. When they interact with an atom in the ground state, atom will essentially absorb this photon because this is resonant to this energy difference, and in turn the atom will climb up to the excited state. If this photons instead interacts with an atom in the excited state, then it will stimulate this atom to come down to the ground state and release another identical photon, the so-called stimulated emission. Now, as the population, the ground state is more, therefore, this beam of light as this traverses through the medium will interact the ground state population more frequently than the excited state population. And whenever there is an absorption, there is an interaction of this beam of light with the ground state, there will be an absorption. So one photon will be removed from this incident beam, it will be absorbed. But whenever they interact with the atoms in the excited state, as a result of stimulated emission, one photon, identical photon, will be added to this group of photons. And now, because population, the excited state is less, so there will be more absorption than stimulation. And therefore, there will be gradual diminution of number of photons from this incident beam of photon, and thus, as it emerges through the medium, it will be at attenuated output beam. Thus, quite expectedly, the medium here behaves like an absorber. We now consider the second case, where let us assume that initially we have created a condition where the excited state has more population than the ground state. Now, as this beam of light containing identical resonating photons travels to the medium, they will of course interact more frequently with the excited state than in the ground state. And thus, more and more identical photons will be added to this incident beam of light, then the photons will be removed from it as a result of absorption. Thus, an amplified beam of light will eventually emerge through this medium. Thus, you see, amplification of light is possible if and only if the initial population exceeds initial population of the excited state exceeds that of the ground state, a condition that is normally termed as population inversion. However, such a situation violates the rule of nature and thus cannot come about naturally. In reality, therefore, the population in the excited level is always lower than that in the lower level, unless the mechanism to invert the population, a trick not so easy to realize, is in place. In an ordinary fluorescent tube, tube light, although the electric discharge succeeds in transferring a fraction of the ground state population into excited atoms, the condition of population inversion is not met. The amplification of light thus is not possible, because if there is no population inversion, amplification is not possible. There will be more absorption from the ground state than there will be stimulated emission from the excited state. Therefore, that we thought that a tube light also should be able to amplify light is impossible. Therefore, there will be predominance of spontaneous emission in a tube light discharge, spreading the light in all direction and making it possible for us to use such a device as a viewing source because it would spread light in all possible direction. It would be pertinent here to consider third case where both the excited and the ground state have equal number of populations. And therefore, when this beam of light comprising that bunch of identical resonating photon travel through this medium, then they will interact with same probability with the excited and ground state, and therefore same number of photon would be removed from this medium as a result, beam of light as a result of absorption. What will be added to it as a result of stimulated emission, and therefore it will pass through it unaffected. The medium, therefore, behaves like a transparent window through which the input beam passes unhindered. This situation, like the case of population inversion, is also a violation of the rule of nature. And the ways of experimentally realizing a population inverted condition will be addressed later during this course. Thus, a light amplifier can be pictured in the following manner. You have an inverted medium, that is a medium in which you have inverted population between two energy levels. And you shine this medium by a bunch of identical, that is coherent, resonating photons. Now, as this photons travels through this inverted medium, because the population in the excited state is more, therefore the medium, by virtue of stimulated emission, would add more and more identical photons to this incident group of photons, then the number of photons that will be absorbed, removed from it due to absorption, or in other words, it would give out an amplified coherent light. Thus, the medium behaves like a light amplifier. It amplifies light, not an electronic amplifier. Now, it is quite understandable that higher is the population inversion. That means more and more number of species, if you can transfer in the excited state, that is, you are increasing the population inversion, there will be more amplification because there will be rate of stimulated emission will be more as the number in excited state is more. So the power of this optical amplifier increases with increasing population inversion. Or in other words, we can say that the gain of this optical amplifier increases with increasing population inversion. Now, a laser is an acronym for light amplification by stimulated emission of radiation. Therefore, a laser also amplifies light. But surely it does not require an input coherent source for its operation. If it did, then the laser would have lost almost all its charm. So how does it work? It amplifies light, yet it does not require an input coherent source of light for its operation. Well, to understand this, we must know what is the cavity. Let me end here today, and in the next class, we will provide a simple physical insight to explain to you what a cavity is.